Okay, we're going to go ahead and try problem 29, and that's located on page 526. We have got a system of system of equations here. Those make up planes, and we're going to see what happens with the solution of these planes. Okay, let's start out by labeling so we know what we're talking about. I'm going to call the first equation A, the second one B, and the third one C. I'm going to start out by eliminating the variable x using equations A and B. So if I multiply equation A by -2, I end up multiplying everything by -2, so I get -2x minus 4y plus 14z is equal to -2 times -4, which is 8. I'm going to add that to equation B. And so I'm going to write equation B, and it's 2x plus y plus z is equal to 13. Adding these two equations together, I eliminate the x. I get a -3y plus 15z is equal to 21. I observe that I get a common factor of 3 in every variable, so I'm going to eliminate that 3. If I had all negatives, I might eliminate a -3, but since these are a mix of positive and negatives, I'm just going to make this a little bit easier to work with down the road. So let's take a 3 out, and I left with -y plus 5z is equal to 7. So that's a pretty simple one to work with, and now I'm going to call that equation D. I'll come back to that later. So now let's eliminate another variable if we can. I'll look at equation A and C, and again I could develop another equation by multiplying equation A by -3. So I'm going to say -3a, and I'll rewrite that as -3x minus 6y plus 21z. And remember, I'm multiplying by -3, so that would be a positive 12 here. -3 times -4. I'm going to bring down equation C now, rewrite it, and then I'm going to combine the equations together and see what happens. Let's do that. We've again eliminated x, and our goal is to have two equations with two unknowns by eliminating the same variable. So I end up here with 3y, and then this would be 36 minus 21 is a -15z, and that's equal to a -21. Okay, I see again I have a 3 as a common factor, so I'll rewrite this without the 3, and that's -7. Okay, so I'm going to call this equation E. Now I'm looking at equation D and E now, and I notice that they're really the same equation. If I multiply E by a -1 on both sides, I get the exact equation as D. So it turns out that in this system, I really haven't eliminated a variable. So what I'm going to do is I'm going to now solve for y in terms of z. And I will then see what I can obtain. It does not appear that I have enough equations to reduce this. So what I will do now is I will solve this for y, and I get y is equal to 5z minus 7. Okay, so that's one equation that relates z to y. Now what I can do then is take a look at another equation and then put x in terms of just z. If z is call it the one independent variable I'm going to keep in this equation. So let's do that by just looking at equation A. So I'm going to take equation A, and what I'm going to do is I'm going to put all the y's and z's on the right side and then see what x equals. So I'll start out by taking equation A, and I'll kind of massage it a little bit. I'm going to take and write it as x is equal to -2y plus 7z, and that's -4. Now what I'm going to do there is I'm going to substitute this y equals 5z minus 7 into this equation, and x is equal to negative 2 times 5z minus 7 plus 7z minus 4. I'm going to simplify it up now by distributing, and then I have 10z, let's say that's negative 10z, plus 14 plus 7z minus 4. Okay, and so what I'm left with then is x is equal to a negative 3z plus 10. So if I choose to leave z as my independent variable, what I would get as a solution for this would be all in terms of z, and I could write this negative 3 and call this z my independent variable. The book likes to call it a, so I will just put a here, and plus 10, and then my y would be 5a minus 7, and then finally my z is my variable a, and so then that would be my solution.